Welcome back to Multivariate Calculus. In this video, we're going to be talking about conservative vector fields. We've mentioned the idea of conservative vector fields before. Conservative vector fields were the first kinds of vector fields we looked at. Any vector field formed by taking the gradient of a scalar function is a conservative vector field, and in fact, that is the definition. A conservative vector field is any vector field that can be written as the gradient of some scalar function, which we call a potential function. We've also talked about vector fields, and I've mentioned the relationship between vector fields and force fields. Right? Force fields are certainly the most common kind of vector field, and most of the calculations that we're doing on vector fields have applications specifically in forces rather than other types of situations. Not to say that there aren't other kinds of vector fields, but the calculations that we're going to be doing are by and large force calculations in physics. So that's what I want you to think of whenever you think vector field, think force field. Now, before we can continue onward, I guess it's worth taking some time and going back and thinking about physics, because the idea of conservative and conservation comes up quite a bit in the physical sciences. One thing that can start to be confusing when you start talking about conservative versus non-conservative forces is that there is nothing in a force itself which is conserved. There are several things that are conserved in physical systems. The total mass of the system is conserved. The total momentum of the system is conserved, and the total energy of the system is conserved. That last one is the one that I want to pay attention to. Of course, in modern physics with relativity and E equals mc squared, energy doesn't have to be conserved because energy can become mass and mass can become energy. But we're thinking very much in a classical regime physics sense here, something that you can see in everyday life. So energy is conserved in most systems. In a closed system, all energy is always conserved. In practical situations, a closed system is very hard to come by. Most systems are what we call open systems because some energy can be lost. Loss of energy frequently happens in the form of heat and in the form of sound. As an example, reach over here and grab my favorite toy, a Slinky. A Slinky is noisy. When you play with a Slinky, it creates noise. That noise is energy in sound waves that reach your ears. Creating sound waves loses energy from the system. That's dissipation. Another thing that will happen, if you play with a Slinky for a while, it will eventually start to get warm. Heat dissipates. That is a very common form of energy loss. More extreme example of that, I'm recording this video and all of these videos on a computer that has a pretty intensive fan on it that is blowing heat in my face. The purpose of blowing that heat out of the computer is to allow the processors to cool off, and so that they don't increase friction. Friction with electrons increases as the heat increases. Friction with most things increases as heat increases. So keeping things cooler reduces friction. Friction causes heat. It's a runaway effect. Right. So forces like friction will cause dissipation of energy in the form of heat. When friction is something you have to take into consideration, force or energy is no longer conserved. So we call friction a non-conservative force. Compare that to something like a spring constant. As I stretch the spring, the Slinky, out, it wants to compress back in. We can describe that as a potential energy. The kinetic energy of actively stretching this out, converts into the potential energy that is the spring being stretched. And if I let go, it springs back into place, releasing the potential energy, turning it back into kinetic energy. The spring then hits the stop and it stops moving, releasing that energy in the form of sound and heat and a little bit of pain because it pinches my finger. Similarly, if I take the slinky and I hold it up into the air, raising the slinky up is introducing gravitational potential energy. And if I let the slinky go, it moves. The gravitational energy turns into the kinetic energy of motion, which is then stopped by the spring force. But if I keep going, it will keep moving until it hits something. I wish I had something a little bit easier to see than this die, but I think that shows a little bit better what's actually happening. When I toss the die into the air, I impart kinetic energy in the form of velocity. And as the die raises out of my hand, it slows down until it reaches a stop somewhere around here. At that point, all of the kinetic energy has converted into potential energy. Then the potential energy starts converting back into kinetic energy and it strikes my palm with about the same speed as when I threw it in the first place. A little bit of that energy is lost to friction, but most of the energy is conserved. So the spring force and the gravitational force are two examples of conservative forces. Conservative forces have potential energy functions. In mathematics, we want to be a little bit more generic, so we call generically vector fields, and we call generically potential functions. But I want you to keep in your mind force and potential energy, and the mathematics all works from there. So now that we know what's going on, let me get my head out of the way and let's look at the actual definitions. We say that a vector field F is conservative if and only if there exists a potential function phi such that F is the opposite of the gradient of phi. That opposite of, technically speaking, is not necessary in the mathematics, but speaking as a person who learned this idea without that negative sign and then went on to study the same idea in physics, it really threw me off. So I go against most calculus textbooks and I throw that negative sign in. It helps with the idea of energy in physics by making potential energy larger the further you go away from the source. So something that is higher off the ground has more gravitational potential energy than something that is closer to the ground. We can do this in 2 dimensions or in 3 dimensions. So if we have F going from R3 to R3, then the potential function phi has to go from R3 to R, and we get that F of X, Y, and Z is the negative of the gradient of phi of X, Y, and Z. And that certainly works, and there's nothing that changes when we go into that compared to the 2 dimensions that we're going to predominantly look at. But 2 dimensions is easier because it's a lot easier to graph. So we're mostly going to be looking at vector fields that go from R2 into R2 and potential functions that go from R2 to R. So if we have our vector field f of x and y is equal to the negative of the gradient of phi of x and y. And nothing that we do is going to depend on whether there's x and y or x, y, and z, with one exception, which is going to actually be the first thing we do. But that's okay. The easiest way when you have a two-dimensional vector field to determine if the field is conservative or not is to rely on Clairaut's theorem. The second partial of phi with respect to y then x, or with respect to x then y, should give you the same value. And we can look to see if that actually happens by differentiating. Well, we know that minus del phi is the negative of partial of phi with respect to x and the negative of partial of phi with respect to y. And that's what f is. So if we take our vector field f and write it as components, f of xy, little g of xy, and we take the partial derivative of little f with respect to y, and the partial derivative of little g with respect to x, then what we're really doing is taking the partial of phi with respect to x and then differentiating with respect to y, taking the partial of phi with respect to y and then differentiating with respect to x. And by Clairaut's theorem, these things should be the same. If they are, then a potential function exists. If they are not, then a potential function does not exist. Black and white. So for example, let's take a look at the function f of xy given as y negative x. This is the vector field that we've looked at previously. We found that it kind of had some annoying properties. But notice that if we take the partial of the x component with respect to y, we get 1. And if we take the partial with respect to x of the y component, we get negative 1. Those are not equal to each other. So this vector field is not conservative. By comparison, if I take some other vector field, g of x and y, x over x squared plus y squared, y over x squared plus y squared. And I take the partial derivative with respect to y of the x component, which is not going to be fun, but not nearly as bad as it seems because that x in the numerator is a constant. So we really have x squared plus y squared to the negative first power. And taking the derivative there, we're going to have that same thing to the negative second power, and then the derivative of what's inside there, which is just 2y. So I get negative 2xy over x squared plus y squared, the whole thing squared. Now, if I take the derivative with respect to x of the y component, y over x squared plus y squared, I get constant y, x squared plus y squared to the negative first, multiplied by the power negative 1, raised to the next lower power negative second, multiplied by the derivative of the stuff inside. Derivative with respect to x of x squared plus y squared is 2x. And simplify this, we get negative 2xy over x squared plus y squared squared. These two things are in fact the same. So this vector field is conservative. Now that we know that this vector field is conservative, maybe we'll be able to figure out what the potential function that created this vector field is. So I'm going to come back up here. I'm going to copy the function itself onto a clean sheet so that I can continue working with it. And now my instructions are find the potential function phi such that g is the negative gradient of phi. And do we really need the negative? No, not necessarily, but it makes things feel more physicsy. In fact, it actually makes the math a little bit harder, so sometimes it's better to leave that off. So let's find the potential function phi so that g is the gradient of phi, and we won't worry about whether it's positive or negative. We'll deal with that at the end of this whole process. Well, I know that the partial derivative of phi with respect to x must be x over x squared plus y squared, which means that phi itself must be the integral of x over x squared plus y squared with respect to x. Right? Taking the derivative of phi with respect to x and integrating with respect to x should cancel each other out. All right, to perform this integral, it looks really intimidating until you realize that if you let u equal x squared plus y squared, and remember that y is constant with respect to x, that du is 2x dx. So this really is 1/2 the integral of du over u. The integral of du over u is the natural log of the absolute value of u. U itself is x squared plus y squared, which is always positive. And I guess I can take that 1/2 and bring it inside the log. It's a little bit more sensible to write this as the natural log of the square root of x squared plus y squared. Although there's something that I do have to worry about. Because whenever I perform an indefinite integral, there's always some constant of integration. But because I had a partial derivative up here, my constant of integration is more complicated than we usually think of it as. Because I integrated with respect to x, and I assumed right here, I assumed that y was constant. Which means that my constant might actually be a function of y. And that's something that can be a little bit tricky. In this particular case, it's not that big of a deal. To figure out what that constant is, I can go back to my original definition, and I know that the partial of this function with respect to y, I can just calculate derivative of natural log is 1 over the argument times the derivative. Derivative of x squared plus y squared with respect to y is 2y. And I'm actually differentiating this line, not the last line. It's a little bit easier to take the derivative of. And by playing a matching game, I know that I was supposed to get out y over x squared plus y squared. I wasn't supposed to get a c prime of y. So that last term is 0. That makes my life a lot easier. So in fact, my phi here is a constant. Now I know my potential function. We'll come back and look at this in a little bit more depth. I have one more question that I want to ask on the same function. But before that, I want to look at things in general. A line integral for a vector field changes depending on the path. We saw that in earlier examples. We looked at two paths that went from the point 0, 0 to 2, 4, and saw that both of those integrals gave us different results. If the vector field is conservative, I claim that the line integral depends only on the endpoints and not on the path at all. That's a bold claim, and a bold claim in mathematics is deserving of a proof, so let me do just that. For a conservative vector field, f is the gradient of phi. The path integral f dot dr is equal to phi evaluated at b minus phi evaluated at a, where a and b are the endpoints of the path. And I guess I'm thinking about these things as vectors. So a and b have x and y, or x, y, and z components. I'm evaluating at the endpoints. This is the fundamental theorem of line integrals. And you should recognize that it looks very similar to the fundamental theorem of calculus. The integral of f prime of x is equal to f of b minus f of a. It's the exact same thing, except we're talking about a gradient instead of a derivative f prime. Right? But I claim that we can prove this. And so let's take a look at the integral f dot dr, which I can rewrite as the integral of the gradient of phi dot dr. And I can then rewrite this taking phi and evaluating it at r of t. And then dr is, of course, r prime of t dt, right? So using the chain rule and a substitution, if r is a function of t, then dr is r prime of t dt. It's just a u substitution using r and t instead of u and x. Right? But then from here, using the chain rule further, the gradient of a function along a path is in fact the derivative with respect to t of f of r of t All right, unpack that a little bit further. If I want to take the derivative with respect to t of f of r of t, then I need to take the derivative of f, or I'm sorry, it's derivative of phi evaluated at r of t, and then chain rule multiply by the derivative of r. So using the chain rule, I've rewritten this as an ordinary derivative with respect to t. Now that it's an ordinary derivative, I can use the ordinary fundamental theorem of calculus in order to rewrite this. All right, so let's consider again the vector field we've been looking at. G of x and y is x over x squared plus y squared, y over x squared plus y squared, and we found that the potential function here was half the natural log of x squared plus y squared, plus some arbitrary constant, but we don't really care about what that arbitrary constant is. All right, so I would like to evaluate the integral, the path integral, g dot dr, for my path r of t going from cosine t sine of t, t between 0 and pi over 2. And I could go through and deal with all of the things that I've dealt with before, substituting those values in for my x and y coordinates is not nearly as bad as it seems. Mostly because x squared plus y squared equals r squared, and r squared in this case is 1, so things will simplify pretty quickly. We could do this the brute force approach. But I can also notice that this is the integral. When t equals 0, I'm at the point 1, 0. When t is pi over 2, I'm at the point 0, 1. So by the fundamental theorem of calculus, this is going to be the integral. This integral is going to be phi evaluated at 0, 1 minus phi evaluated at 1, 0. All right, plug in x equals 0, y equals 1. You get natural log of 1, which is 0. Plug in x equals 1, y equals 0, you get natural log of 1, which is 0. So we have 1/2 natural log of 1 minus 1/2 natural log of 1. I'm picking c equals 0 because it's the most convenient version of this potential function to work with, but I could pick any value of c and this would still work out. And I get 0. That's really convenient. All right. So here's one I would like you to try. I'm going to use the same function g, whose potential function we've already found, and I would like you to evaluate the integral g dot dr along the curve defined by the parametric system t cubed with 0 less than or equal to t less than or equal to 2. See what you can do with that one, and I'll see you in the next video.